Hello everyone, I'm Paul and today we're solving problem 3454, separate squares 2. This is a very hard problem, or at least it was for me, so next I will show you how to solve it visually and then we'll go with the code. If you haven't seen part 1 yet, I highly recommend you to go and watch that video first. It's in my channel. This is very similar to part 1. We are given a 2D integer array squares where each element has 3 numbers. The first 2 correspond to the bottom left corner of the square, and the third one is the size or length of the sides. So if we are given this element, we have this square. And we need to find the minimum value for y that splits the total area of the squares in 2 equal parts. So the area above the line should be equal to the area below the line. In this case, the result is 1. This is the minimum value for y, for which we have an area of 1 below the line and an area of 1 above the line. Given that these are equal and this is the minimum possible y, we just return 1. Now the only difference with part 1 is right here. Squares may overlap, and overlapping areas should be counted only once. So, if we are given this input with 2 squares, we have one big square here and a small one here. Overlapping areas should be counted only once, so this area should be counted only once. If we take 1 for y, now we're splitting the squares here, the area above is 2 times 1. Remember that we get the area of a rectangle by multiplying side by side. So the area here is 2. And the area below the line is 2 times 1, which is 2. Given that we have equal areas and this is the minimum possible value for y, we return 1 in this case. Maybe you are thinking about running a binary search to try different values for y. So if y is here, we are splitting the squares at this point. And we need to compute the areas above and below the line. The area above the line is easy, that's what we did in part 1. For the area below the line, if we compute overlapping areas, this is also easy, that's what we did in part 1, but here, overlapping areas should be counted only once. So we need to count this only once. This means that we need to think about this as one unique shape. Now, how do we get the area of this shape? As you can see, this might become very difficult. So what we can do instead is the following. Here we are using something called line sweep plus segment tree. And this is a pretty advanced topic, so I recommend you to think about this step by step. For the line sweep part, we are iterating different values for y with breakpoints. This is one breakpoint, this is another one, this is another one, and this is another one. We are iterating this from bottom to top, so we start here, and we are using a segment tree to keep track of the covered intervals of x at every step. So first we are here, and right now the covered interval is this one, because of this line from this square. Now we are at the next breakpoint, and every time we are computing the area below the current breakpoint. Here we have this, which is given by the size of the covered interval times the current breakpoint minus the previous breakpoint. So now we have this area. And given that we are standing here, now the covered interval goes from this point all the way to here. Why? Well, because we already had this from this square. Now we are adding the base of this square, all of this. So now we can go from here to here. We have all of this covered. Now we are at this breakpoint, so we need to compute the area below this breakpoint. We compute all of this. How do we get this area? Well, we need to take the covered interval up to this point times the current breakpoint minus the previous breakpoint. The area is always side times side. So now we have this area, And now we are reaching the top side of this square. So at this point, we need to remove this part of the covered interval. Now we are here. The covered interval goes from this point to this point. So we have this. Now, how do we get the area of this? Well, we take this times the current breakpoint minus the previous breakpoint, and that's how we get this area. So now with this, we have already computed the total area. And now we can run the exact same process again. So here we don't have any square below this breakpoint, so we can just compute this interval, and now we have covered this. We move to the next breakpoint, and now we can compute this area by taking this times the current breakpoint minus the previous one. We always do side times side. Now we have this area, and now we're checking if this is greater or equal to the total area divided by 2. That's how we know that we have already computed half of the area, because if we find the scenario, we can return the result. So let's say that this area is not big enough. We are still here, so we need to add this to our covered range. So now the covered range goes from this point to this one. Now we are at this breakpoint. We need to compute the area below this breakpoint, so we compute this, and we do this by taking the covered interval times the current breakpoint minus the previous one. That's how we get this. And now let's say that this area is equal to total divided by 2. Now we can get the result. At this point, we can return this y. So this is a big overview of our algorithm. We are running this process 2 times. Now let's see an example. Let's say that we are given this input again. First, we are building our segment tree. And remember that we are using this to store segments regarding the x-axis. So what are the possible values of x here? Well, we have 0, 1, and 2. So this will be the base of our segment tree. And what are the minimum segments that we can have here? Well, we can have one segment from 0 to 1 and another one from 1 to 2. So think of this as if we had 2 nodes here. This node covers the range from 0 to 1, and this node covers the range from 1 to 2. And here we have a parent that covers everything from 0 to 2. And we will say that this is position 0, this is position 1, and this is position 2. Let's say that we are standing at position 0 and we want to check what's the result of position 1. Well, we take the current position times 2 plus 1. That's how we get 1. If we are here and we want to reach the result of this node, we do 0 times 2 plus 2. That's how we get this position. And from each node, we want to keep track of 2 things. The count of squares that cover this range, this is initially 0, and the length of the interval that's covered by this range. This is initially 0 also. So now we can start with our line sweep. First, we are here. Remember that these are our breakpoints. We are iterating this in order, so first we are here. And now we have a square that goes from 0 to 2 regarding the x-axis. So it goes from 0 to 2. And we need to find the largest possible interval that's covered by this square. And here we always start from the root. We are checking if we can fit this interval inside this square. So here left is 0, and this happens to be equal to the left bound of the square. And right is 2, which is also equal to the right bound of the square. So we can fit this here. So in this case, we have a full overlap. This means that we can cover this entire interval, meaning this interval, with the current square. So we add 1 because this is the first square that covers this interval. And this is the length of the covered interval. So we do right minus left. That's how we get this length. So this is 2. Now here we put the 2. Now we are at this breakpoint, so we can compute the area below it. We can compute all of this. How do we do this? Well, here at the root, we have the total covered interval for this entire input. We know that it's 2. Right now, regarding x, we have this covered. And this side is given by the current breakpoint minus the previous one. So we do this times 1 minus 0, and the result is 2. So the area here is 2. So the total area up to this moment is 2. And we are here because of the base of this square. So now we need to add this to our segment tree. So we are dealing with this square. We want to find the largest segment that we can fit into this square. And we always start from the root. This goes from 0 to 2, so from here to here. And given that 0 is smaller than the left side of our square, here we have a partial overlap. This means that we can shrink the current segment. We can try smaller segments to see if we can fit any of them into this square. How do we do this? Well, we can just move down one level and explore these two nodes. So first we are here. Given that the right bound here is equal to the left bound of the square, well, we can't fit this segment into this square, so this will just return. Now we are here. This segment goes from 1 to 2, and we can fit this into our square, so we are good to go. Here we have a full overlap again. So the amount of squares that can cover this segment is 1 now, and the length of the covered segment is given by right minus left, and 2 minus 1 is 1. And maybe after updating this node, we should update the root. But that's not the case here, because we have one square that's covering the root. And the segment of the root is greater than the current segment, so we can leave this as it is. The covered value here stays at 2. And you can see why here in this drawing. The covered value up to this point stays at 2 because we still have this base. And this is represented here. We have one square that covers a length of 2. So now we are at this breakpoint, meaning we can compute this area. How do we do this? Well, for this side, we have the covered length right here in the segment tree at position 0. We know that it's 2. And this is the current length of this side. And this side is given by the current breakpoint minus the previous one. So we do this times this, and the area for this part is 2. So we add 2 to total area. This is now 4. And we are still at this breakpoint. So here we need to remove 2 squares, the big one and the small one. Let's start with the big one. We have to remove this square. So we are looking for the largest segment that we can fit into this square. We always start from the root. This goes from 0 to 2, and we can fit this into our square. So now we can remove one square at this point. We subtract 1 from here. This is 0 again. And now the new covered length is given by the sum of covered in the children of this node. So 1 plus 0 is 1. The new covered length is 1. And this makes sense. If we look here, when we remove the big square, now we are left with only the small one. So the covered length here is 1. And we are still here because we need to remove the small square also. So we need to remove this. We start from the root, and here left is smaller than the left side of the square. This means that we can move to the next level. We can try smaller segments to see what's the largest full segment that we can fit into this square. Next we are here. This is out of bounds because it goes from 0 to 1, so we can't fit this into our square. Next we continue with this one. We can fit this here, so now we can remove one square from this segment. This is now 0, and the new covered value at this point is 0. And now, given that in the root the count is 0, we need to update the value for covered. This is the sum of 0 and 0, which is 0. So now we have already tried every breakpoint and the total area is 4. Now we can repeat the same process to check what's the minimum y that has exactly half of the total area. So we will have another variable which is accumulated area. This is initially 0, and we are iterating breakpoints again. So we start from this one. We don't have anything below this line, so this stays at 0. And now we need to add this to our segment tree. So we are adding this square. Now we always start from the root, and this segment goes from 0 to 2. We can fit this into the current square, so here we have a full overlap. The count here is 2, and the covered range goes from 2 to 0. This is 2. So now we can continue with the next breakpoint. Here we can compute the area below this breakpoint, so we take the covered range for position 0, which is 2. This corresponds to this length, and regarding this length, we take the current breakpoint minus the previous one. So 2 times 1 minus 0, meaning 1, is 2. The area of this is 2, so the accumulated area up to this point is 2. So now, given that the accumulated area is equal to the total area divided by 2, well, we know that we have exactly half of the total area below the current breakpoint. So the result in this case is 1. Now let's say that here we have a 2 instead. This means that we have something like this, and here we will have these breakpoints. And let's say that we implement the same process. We are iterating breakpoints. First we get the total area, next we iterate this, then we iterate this, and at this point we realize that we have more than half of the total area. So how do we reach the result 1.5 in this case? And we need to use some algebra for this. We know that the accumulated area up to the last breakpoint plus sum of the current area, meaning the area from the current breakpoint to the previous one, should be equal to exactly half of the total area. Okay, so with this we can say the following: the accumulated area plus some part of the current area, which is given by the combined width times the last gap to mid, should be equal to total area divided by 2. This means that this chunk is equal to the accumulated area, which is down here, plus the current area, which is the combined width, meaning this width, times the last gap to mid, this gap. This should be equal to total area divided by 2. This would be the total area, and this divided by 2 should be this. So now we can solve for last gap to mid. So we say that this is equal to total area divided by 2 minus the accumulated area, and we need to divide this by combined width. So now we can say that the smallest y is the previous y plus last gap to mid. That's how we get the smallest y. This is exactly what we are doing in the code. And just to be clear, last gap to mid is this small gap, and the previous y is this gap below. So if we add previous y and last gap to mid, we get the minimum y that splits the total area in exactly 2 equal parts, which is 1.5 in this example, so we return this. So once again, for the second loop, we are iterating breakpoints, and as soon as we see that the current accumulated area is greater or equal to the total area, we can implement this and get the result. Now, regarding time complexity, we need to iterate squares. We know that this requires big O of n, where n is the amount of squares, and we need to run operations on our segment tree. Each of these will require log n time complexity, and maybe you are wondering why. Well, let's say that we decide to update this node. Now potentially we need to update the parent, and potentially we need to update this parent also. And given that this is just a binary tree and we have one parent per node, well, here this will run in at most log n time complexity. The height of this tree is log n. And we need to sort unique values for x. Let's say that this requires m log m, where m corresponds to unique values of x. And we need to sort breakpoints for y. This requires n log n because that's the time complexity for sorting. So we can say that this is the required time complexity. And space complexity is big O of n because this is required for sorting. And also we are building events from these squares to be able to implement our line sweep. So with this in mind, now let's go with the code. First, we can start with our segment tree. So we go up here and we say class segment tree, and this has a constructor. In Python we use init, and this takes self, and we have an array with unique values for x. We'll call this xs. And just to be clear, this is a list with integers. Now we say self.xs is xs. Self.n is the amount of segments that we have. This is the length of xs minus 1. Self.count is an array with 0 times the maximum amount of elements that we can have in the segment tree, which is 4 times self.n. And we are doing the same for cogrid. So we can just copy this, and this is cogrid. Now, we need a function to update segments. So we'll call this update, and this takes the square left, square right, a left bound for the current segment, a right bound, and an operation type, which can be either 1 or -1. We are using 1 if we add a segment, else we use -1. And the current position, we start from 0, meaning from the root. So if the square right is smaller or equal to the left bound of the current segment, meaning self.xs at left, or if the square left is greater or equal to the right bound of the current segment, meaning this is self.xs at right plus 1, here we just return. And just to be clear, here we have no overlap. And maybe you're wondering why are we using r plus 1 instead of r. And that's because left and right are indices, but we want to store intervals in this segment tree. So we need to add 1 to right. Now, what if we have a full overlap? Here, if the square left is smaller or equal to self.xs at left, and the square right is greater or equal to self.xs at right plus 1, well, in this case, we have a full overlap, so self.count at the current position plus equal the current operation type, which can be either 1 or -1. And here we have a full overlap. else this means that we have a partial overlap. So in this case, we can take a midpoint. This is left plus right, divided by 2. We need to round down this. And now we can call this function for our children. So self.update with square left, square right, left, mid, the current operation type, and the position of the left child is position times 2 plus 1. And we need to do the same for the right child. So here we go from mid plus 1 to right. The operation type is the same, and the new position is position times 2 plus 2. Now this works like a post-order traversal DFS. This means that first we need to call this function for our children, and then we need to do whatever we need to do on the way up to the root. So if self.count at the current position is greater than 0, this means that self.covered is now this is at the current position. This is now self.excess at right plus 1. Remember that this is very important, minus self.excess at left. So if we ever reach this scenario in which we have a full overlap, well, now the count for the current position is greater than 0, so we can say that covered at the current position is the range for the current segment. So else if left is equal to right, we can say self.covered at the current position is equal to 0. Else we can say self.covered, I will copy this, at the current position is equal to self.covered for the left child, position times 2 plus 1, plus the right child, position times 2 plus 2. And now we need another function, query. This takes self, and we are using this to return self.covered at 0. So this will return the range that's covered at every step. And I'm realizing that I have a typo here. This is square left. So now we can continue with the main function. First, we need a variable to store unique values for x. So we'll call this xs. This is an empty set. And we will have an array events that's empty initially. You will see why in a few seconds. And now for x, y, and size in squares, we add to xs x, and we need to add the right side, meaning x plus size. And events.append, and here we add an array that includes first the breakpoint. Here we are adding this segment, so the breakpoint is y. Next we need to add the left and right sides, which are x and x plus size, and we need to add the current operation, which is 1. Here we are adding the segment. Just to be clear, here we add segment. Now once we reach y plus size, we need to remove the segment. So this is y plus size, and this is minus 1. And just to be clear, here we remove the segment. Now we need to transform xs into a sorted array. So here we use sorted xs, and we need to sort the events by index 0. So events.sort, and this sorts by index 0 by default, and we have the breakpoint in index 0. So this is exactly what we want. We leave it like this, and now st is equal to segment 3 with xs. Now we can start with the first loop. Here we need to get the total area. So total area is initially 0, and the previous breakpoint is initially events at 0, 0. So now we can iterate events, for y, square left, square right, and operation type in event. We need to add to total area. The covered range up to this point regarding the x-axis, this is st.query times y, meaning the current breakpoint minus the previous breakpoint. And now we need to update our segment tree, so st.update with square left, square right, and the left bound for the segment initially is 0, the right bound is initially the last segment, st.n-1, and remember that we are adding 1 to right in our segment tree class. So here we need to subtract 1. And the operation type is the current operation type. This is given by the current event, and we start from position 0. And now the previous breakpoint is the current breakpoint. So in the first iteration, this will be 0. So we will add 0 to the total area. And from the next operation, we will add positive numbers to total area. So now we can start with the second loop, where we get the smallest y for first half of total area. So here we get the result. The accumulated area is initially 0, and the previous breakpoint is initially event 0, 0, same as before. So now we can iterate events again for y, SQL, SQR, and operation type in events. We have a combined with, which is st.query, and the current area is current with, this is combined with, times the current breakpoint minus the previous breakpoint. Now, up to this moment, we are doing the same as before, but here we can check if at any point the accumulated area plus the current area is greater or equal to the total area divided by 2, now we can get the result. I will copy what we did before just for reference, and here remember that we can get the last gap to mid, and with this we can add the previous breakpoint with last gap to mid. That's how we get the smallest y. This is the result. So here we just return the previous breakpoint, meaning this, plus last gap to mid, which is this part up here. So I will copy this, we add this here, and if we are still here, this means that the accumulated area plus the current area is smaller than half of the total area. So in this case, accumulated area plus equal current area, and we need to update our segment tree. So st.update with SQL, SQR, we go from 0 to st.n-1. The operation type is given by the current event, and we start from position 0. And we say by is equal to y, same as before. So this is the entire code. Now let's submit this and see if it works. As you can see, this works and it's very efficient. This is a very long code, so you can pause the video here to copy this first part, and now you can pause the video here to copy the second part. As you can see, this was a very long and hard problem, so if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.